Hi there, this video is section 4.4 part 2, the mean value theorem for integrals and average value of a function. So in section 4.2 we saw that the area of a region under a curve is greater than the area of an inscribed rectangle and less than the area of a circumscribed rectangle. Right, we used those type of rectangles when we were calculating lower and upper sums. So the inscribed rectangles give us the smallest area, depending on the number of rectangles that you're using. So like if we thought about using one rectangle to estimate the area between the curve and the x-axis, and it was an inscribed rectangle, that would be the smallest area that you could use to approximate, right? The lowest, because you would be using the lowest function value. And then if you used a circumscribed rectangle, which would be the upper, correspond to the upper sum to estimate the area bounded between the curve and the x-axis, it would be the largest function value on the interval, and therefore like the largest possible area to approximate. Now the mean value theorem, and the actual area bounded between the curve and the x-axis is a value that's greater than or equal to the inscribed rectangle or less than or equal to the circumscribed rectangle. Now the mean value theorem for integrals states that somewhere between the inscribed and circumscribed rectangles, there's a rectangle whose area is precisely equal to the area of the region under the curve. And here's how the mean value theorem for integrals actually reads. So it says if a function f is continuous on a closed interval from a to b, then there exists a number c in the closed interval from a to b such that the definite integral is equal to f of c times the quantity b minus a. So f of c times b minus a, that represents area of a rectangle that has a height of f of c and then a width of b minus a. So this is mean value theorem. Remember when we were studying mean value theorem for derivatives, which guaranteed a rate of change on an interval, an instantaneous rate of change on an interval. It's an existence theorem. So it tells us that a number exists or a value exists, but it doesn't tell us how to find that value. It guarantees the existence of one value, at least one value c on the interval, such that this statement is true, such that the area of the rectangle that could be created from f of c times b minus a is equal to the actual area bounded by the curve and the x-axis, which is represented as the definite integral. So the mean value theorem sets us up to be able to calculate the average value of a function on an interval from a to b. And here is how we calculate the average value. So if you think back to, you guys know how to calculate the average of a finite number of values, right? Like if we were trying to calculate the average test score in a class, we would add up all of the scores and then divide by the number of tests that had been taken. But what if you're trying to find the average value of a function on an interval where there are infinitely many values? If we think back to that process that we use for calculating the average value of a finite number of values, right? So we would want to add up all the function values. So we would want to do like f of c sub 1, f of c sub 2, f of c sub 3, right? Up to f of c sub, let's say, n. And then we would want to divide by n, right? Where we're thinking about there being n number of values that we're adding up. Now we know that on an interval, a closed interval where a function is continuous, that there's actually infinitely many values. So you can maybe see where we're getting at with this, right? Like if this were then divided by n, and we can rewrite this using summation notation, right? Like, so we could represent this sum as 1 over n times the sum from I equals 1 up to n of f of c sub I. And then if we were to think, and we could leave the 1 over n over next to f of c sub I, or leave it where it is. Now, if we thought about multiplying by a version of 1, because we're not exactly to our definition of a definite integral yet, but so if this were times 1 over n, now if we thought about multiplying by b minus a over b minus a, well, now we're getting closer, right? So this could be thought of as times 1 over n. And then if we pull 1 over b minus a out, let me move this over. F of c sub I times 1, or sorry, that would be b minus a over n. And then we're thinking about infinitely many function values, right? Like, so we're thinking about n approaching infinity. So if we thought about taking the limit, so I could pull out the 1 over b minus a, that's just going to be a constant. And then taking the limit, I shouldn't say that this is equal, but we've set up this sum. So now if we think about taking the limit of this sum, so we would have 1 over b minus a times the limit as n approaches infinity of the sum from 1 to n of f of c sub I times b minus a over n. Well, this is the definite integral from a to b, and then times 1 over b minus a. So this should look familiar, right? This ends up being equal to 1 over b minus a times the definite integral from a to b of lowercase f of x. And if you look at mean value theorem, you're maybe like, well, if we were to divide by b minus a on both sides over here, wouldn't we end up with f of c equals to 1 over b minus a times the definite integral from a to b? So the height of that rectangle that has the same area as the area under the curve is actually the average function value on the interval from a to b. So this is equal to f of c. So using the average value is how you could determine what c is. Okay, so let's look at this example. So given the function 4 times the quantity x squared plus 1, all divided by x squared, let's calculate the average value of the function on the interval from 1 to 3. So average value, I'll say average value, oops, that's not how you spell value, would be equal to 1 over 3 minus 1 times the definite integral from 1 to 3 of 4 times x squared plus 1 all divided by x squared dx. And now to evaluate that definite integral, we can use fundamental theorem of calculus. Before we actually start to integrate though, let's clean this up a little bit. So that would be 1 over 2, and then we can actually pull this 4 out by the constant multiple property for integration. So that would be 4 divided by 2, which becomes 2. And then x squared plus 1 all divided by x squared. Well, that would be x squared over x squared plus 1 over x squared. And the reason that I'm rewriting this is we do not know how to integrate x squared plus 1 all divided, or the quantity x squared plus 1 all divided by x squared. So we have to rewrite in order to use power rule for integration. So that becomes 1 plus x to the negative second power. The 2 is going to hang out here, and now I'm going to integrate. So when I integrate 1, that's x, and then that'll become minus 1 over x, because that would be negative 1 times x to the negative first. And this is why I like to use the bracket notation here, is that I can keep this 2 outside the bracket. So it's going to be 2 times f of b minus f of a. So that'll be 3 minus 1/3 minus 1 minus 1. Okay, so 3 minus 1/3 would be 8/3, and then minus 1 would be my 5/3. Oh no, that ends up being minus 0. Sorry, that ends up being minus 0. So I said that was 8/3 times 2 is 16/3. So the average value of f on the interval from 1 to 3, so the average output, the average y value on the interval from 1 to 3 is 16/3. By mean value theorem for integrals, f of x must be equal to your answer in part A, so equal to the average value for some value on the interval from 1 to 3. Find those values. So going back to mean value theorem, we have solved at this time for what f of c would be. So it's actually easier to use our definition for average value in order to now solve for what c would be, right? Like we know what f of c is. We want to determine what c would be. So we know that f of c will be equal to 16/3. So we want to set our function, so 4 times the quantity c squared plus 1 divided by c squared equal to 16/3, right? That's f evaluated at c equal to 16/3. Okay, if we multiply by c squared on both sides, distribute that 4, so we'd have 4c squared plus 1 equals to 16/3 times c squared. And then if I want to subtract by, what do I subtract by 16/3 on both sides? You know what? I don't want to do that. I want to multiply by c squared on both sides. I would have gotten there. The mental math was just more. Okay, so multiplying by 3 on both sides here. we would have 12 times c squared plus 1 equals to 16c squared. And then now I can distribute that 12. And now I don't have to think about subtracting fractions. So if I subtract 12c squared from both sides, we'll have 12 equals to 4c squared divided by 4 on each side. We'll get c squared equals to 3. So c is equal to plus or minus the square root of 3. However, we're just on the interval from 1 to 3, so it's only c is only equal to positive 3. Root 3 would be our only value of c. That would give us the average function value. Or in other words, the height of the rectangle that would have the same area as the area bounded by the curve and the x-axis. So here's another problem for average value. So the average value of a function f over the interval from -2 to 3 is -6. So I'm going to write that out. So the average value, which would be 1 over b minus a, so 3 minus -2, times the definite integral from -2 to 3, is equal to -6, okay? And then the average value of f over the interval, so same function, different interval, but from 3 to 5 is 20. So that would be 1 over 5 minus 3 times the integral from 3 to 5. Okay, and we want to know what is the average value of f over the interval from -2 to 5. Okay, so from here, we could say that the definite integral from -2 to 3, 3 minus -2 would be 5, so that'll be equal. This definite integral from -2 to 3 will be -30. And then the integral from 3 to 5, multiplying by 2 on both sides, would be 40. And we want to know what the average value of f is over the interval from -2 to 5. So that would be equal to 1 over 5 minus -2 times the integral from -2 to 5. And then we know from our properties of integrals, of definite integrals, that the integral from -2 to 3 plus the integral from 3 to 5 will be equal to the integral from -2 to 5. So we could say that this is equal to 1 over 7 times, I'll write this all out, the integral from -2 to 3 plus the integral from 3 to 5. And since we know those values, we could say that this would be, sorry, why did I write 5? 1/7 times -30 plus 40, which ends up being 10/7. So 10/7 is the average value of f on the interval from -2 to 5. Okay, calculator active example. So that means if it's calculator active, use your calculator. What is the average value of f, we're given the function f, which looks pretty gnarly, on the closed interval from 1 to 3. So that means average value will be 1 over 3 minus 1 times the definite integral from 1 to 3 of f of x. So of sine of 2x times cosine of 1 plus x, which you do not know how to integrate, which is why you have to use your calculator. So guess what? You just type that all into your calculator. Make sure you are in radians. Okay, so typing that in, that'll be 1/2 times, hit the math button, and then number 9 is definite integral. Put in your limits of integration. And I get approximately 0.369 as the average value. Okay, the next example, the intensity of light at a distance x meters from a source is modeled by the function r, where r of x is equal to k divided by x squared, where k is a positive constant. Which of the following gives the average intensity of light between 4 meters and 6 meters? Sorry, guys, this was an multiple choice question on the College Board website that I pulled from. So I didn't give you the options for the answers. So we'll stop where the answer would have been. Okay, so your function is r of x equals to k divided by x squared. Average value will be 1 over b minus a, which in this case would be 6 minus 4, 6 meters minus 4 meters, times, because we want the average value of r on this interval, where inputs are those distances in meters. So from 4 to 6 of k over x squared dx. Now k is a constant, so we're allowed to pull k out of the integral. So k over 2 times the integral from 4 to 6, and I'm going to rewrite that as x to the negative second power to think about using power rule for integration. So we'll have k over 2 times, that'll end up being negative 1 over x from 4 to 6. And then it's negative 1/6 minus negative 1/4. And then the answer that they had was actually 1/2 they distributed the k in. So you just have to make your answer match what one of the options that's there, right? So minus k over 6 plus k over 4. That's how they left their answer. There are different ways you could simplify that, right? That you could get a common denominator there. Okay, another calculator active problem. So the volume in liters of air the volume V in liters of air in the lungs during a 5-second respiratory cycle is approximated by the model V equals to that equation. Okay, so where the volume is a function of time in seconds. Volume in liters is a function of time in seconds. Approximate the average volume of air in the lungs during one cycle. Well, one cycle is 5 seconds, so we could say from 0 to 5 seconds. So the average value, the average value, which would be the average volume of air in the lungs would be equal to 1 over 5 minus 0, or just 1 over 5, times the integral from 0 to 5 of v of t, or of, I'll write down the rule here. This is calculator active, so we're going to be able to type this into our calculator. Okay, so typing this into our calculator, we will get the average volume on that interval. I need to be careful that I'm typing these values incorrectly. So instead of t's, you're typing an x into your calculator. Okay, and I get approximately 0.532, and this will be liters because it's the average volume of air in the lungs. Volume is in liters. Okay, so this is a longer problem that I took from the College Board, but we had multiple more parts than the 2 parts that I have here. So we're going to revisit this problem, the other parts of this problem, later on in section 4.4, but we have to get through the second fundamental theorem of calculus. But we're going to answer the parts that we can, knowing what we know, knowing fundamental theorem of calculus and average value. So this question is calculator active and says Mary and Chance walk in the same direction along a straight path. For 0 to 20, Mary's velocity at time t is given by m of t equals that rule. And Chance's velocity at time t is given by c of t. Both m of t and c of t are positive from 0 to 20 and are measured in meters per minute. So that means time is being measured in minutes. And then m and c are both velocities that are meters per minute. Okay, Mary is 12 meters ahead of Chance at time t equals to 0, and Mary remains ahead of Chance for 0 to 20. That information is going to be for the other parts of the question. Part A here is asking find the value of 1 over 10, 1/10 times the integral from 5 to 15 of m of t. Using correct units, interpret the meaning of what that statement is. Well, isn't 1/10 the same thing as 1 over 15 minus 5? So this is just the average value of m of t on the interval from 5 to 15 minutes. So it would be Mary's average velocity on the interval from 5 to 15 minutes. So we need to actually find that value, right? Pay attention to what the question is asking. It's not just asking us to interpret, it's asking us to find the value. So using our calculator, I'm going to type in, especially because we don't know how to integrate the equation for m of t yet. So that'll be 1/10 times the integral from 5 to 15 of, I'm using the fraction bar, 6,010 over x squared minus 3x plus 50.5 with respect to x in my calculator. And I get approximately 54.5 409. This is the average value of m, so it'll be the same unit, so meters per minute. So to interpret the meaning, we can say that Mary's average velocity from 5 to 15 minutes was approximately 54.409 meters per minute. At t equals to 10, is Mary speeding up or slowing down? This sounds familiar. Getting a little deja vu. Speeding up or speeding down? Speeding up or slowing down? Well, if you remember, we say that an object is speeding up if its velocity and acceleration are the same sign, SIGN, and an object is slowing down if velocity and acceleration are different signs. So let's figure out what the sign of Mary's velocity is at t equals to 10 minutes. So we want to evaluate m of 10. And we have our calculator, so we can just type this into our calculator. Make sure you are using parentheses or using the fraction bar appropriately. But we are also given that m of t is positive. So we know that m of t is going to be positive. So you can either find the value. So m of 10 ends up being approximately 49.876 meters per minute, which wasn't even necessary because we were given that m of t is positive from 0 to 20. So we know that m of 10 will be positive, greater than 0. So we need to figure out what m prime of 10 would be. And we can use our calculator. This is calculator active, so we can use our calculators. So if you type in math, and then number 8, and we're going to differentiate with respect to x in this case. So type in x for the d over dx. Type in the rule for m of t. So 6,010 divided by x squared minus 3x plus 50.5. And then when x is equal to 10. And we end up with approximately negative 7.036, and that would be meters per minute squared, which is acceleration. So m prime of 10 would be less than 0. Therefore, we could say that Mary is actually slowing down at t equals to 10 minutes. So we can say Mary is slowing down at t equals to 10 minutes because m of 10 is positive and m prime of 10 is negative. So that would be enough justification or something like that. Okay, and then we'll be able to answer the other parts of this question once we've gotten a little bit further into the section.